Well, today we have three topics that we're going to look at. First, we're going to take a little review of some exponent rules that you probably learned in math class. Then we're going to take a second look at scientific notation. We've already talked about scientific notation in an earlier podcast, but we're going to look at it again as it applies to computation, including using scientific notation to make quick work of finding easy estimated answers. Then we're going to look at a feature of the SI measurement system that we've been talking about that allows us to scale the numbers up and down, make them bigger or smaller depending on our needs, depending on what it is that we're measuring. And then last, I'm going to teach you a really powerful tool for converting units, but it's actually also useful for a lot of other things too. You can really do any calculation that's linear using this tool. It's called dimensional analysis, and it's extremely powerful. Let's start out by reviewing this exponent rule. If you have a number x to the a and you're multiplying by x raised to the b power, then the product is going to be x to the a plus b. For example, if I'm taking x squared and I'm multiplying that by x cubed, the result is going to be x to the fifth because 5 is 2 plus 3. Here's another rule. If I'm dividing a number x to the a divided by a number x to the b, then my result is x to the a minus b. So for example, if I were taking x to the fourth and dividing it by x squared, my answer is going to be x to the 4 minus 2, which is x squared. The third rule is that x raised to the negative a is really 1 over x raised to the a. So if I see this number, x to the negative 2, what that really means is 1 over x squared. Now, the reason we went over these exponent rules, just reviewed these a bit, is because we're going to make use of these as we use scientific notation to get quick answers, quick estimates of answers in scientific calculations. We've already talked about this, but we're going to review it again. Scientific notation. This is a way of writing or notating numbers that are really large or really small. And that happens a lot in chemistry. We have these large numbers or very small numbers because the objects that we're dealing with, atoms, ions, molecules, are really tiny, and there are lots of them in even small samples. Here's the basic idea. You recall, every number can be written in the form m times 10 raised to the n, where m is a number that we call the mantissa. The absolute value of the mantissa has to fall in the range of 1 greater than or equal to 1 and less than 10. So it has to be a number that's between 1 and 9.99999 something. It can't be just any number. N is called the order of magnitude, or just simply the exponent. And it is a positive or negative integer. If I'm writing a number whose absolute value is less than 1, in other words, it's a fraction, it's a decimal, then the n for that number, the order of magnitude, is going to be less than 0. If I'm writing a number that's bigger than 10, then the exponent for that number is going to be greater than 0. If I'm writing a number between 1 and 10, I'm usually not going to use scientific notation. So to write a number in scientific notation, you want to move the decimal point until exactly 1 digit remains to the left. And then you write down all the significant figures in the number as the mantissa. So this is something new from the last time we looked at scientific notation. The mantissa can't include any digits except significant figures. So let's take a look at this example. There's an implied decimal point there. I want to move my decimal point to the left in this case until exactly 1 non-zero digit remains to its left. So I'd move it over 1, 2, 3, 4, 5, 6, 7, 8 places. This is a number that's bigger than 10, so 10 to the 8th is my exponent. What's my mantissa? Well, since the decimal point was implied here, all these 6 trailing zeros are not significant numbers. The only significant digits are the 2, the 6, and the 2. So my mantissa is 2.62 and includes those 3 significant figures. Here's another example. This is a number that's smaller than 1, and so therefore my exponent is going to be negative. How negative? Well, let's count. 1, 2, 3, 4. If I move it 4 places, I have exactly 1 digit to the left. That's non-zero. So my mantissa is going to be 1.34 because the leading zeros were not significant, and my exponent is going to be negative 4 because I moved the decimal point 4 places. You try this one. Well, here's your answer. I'd have to move the decimal point 3 places, so that would make it 10 to the positive 3 because this is a number that's bigger than 10. I only have one significant figure here, and that's the 9. So just 9 times 10 to the third. Try this one. Well, here's your answer. Well, this is different than the other one. I still would move my decimal point 3 places to the left, so that would be 10 to the third. But now my mantissa is going to include more digits. Because the decimal point is expressed here, it's not implied, that means all those last zeros were significant, and they have to be included in the mantissa, which would be written then 9.000. It's another one. Here's your answer. I'm moving the decimal point 1, 2, 3 places to the right, so that means it's going to be 10 to the negative 3, because I'm writing a number that's smaller than 1. The leading zeros are not significant, so 1.5 are the only two significant digits. That's my mantissa. Here's another one. Seems like the same number, but it's not. What makes it different is the 0 that comes after that 5 is a significant figure. It had to be written to report precision. So I'm still moving 1, 2, 3 places to the right, and so it's still 10 to the negative third, but my mantissa isn't 1.5 anymore. It's now 1.50. I need to include that last 0. Let's try a few backwards. Write this one in long form. Well, here's your answer. I only have one significant figure, so that's 7. And if I move my decimal point 1, 2, 3, 4 places, that would be like adding 1, 2, 3, 4 zeros. So it's 70,000. And I'm not going to put a decimal point at the end. I'm not going to express that decimal point because I want to retain just one significant figure. Try this one. Well, my mantissa, 7.36, includes all the significant figures. So I write down 736. Now, imagining moving the decimal point, I'm going 1, 2, 3, that's another 0, 4, another 0, 5, another 0. So 736,000 is the number. And it has 3 significant figures the way I've written it without the decimal point at the end. Try this one. 1.3 times 10 to the minus third. Well, 1 and the 3 are my significant figures. Imagining moving my decimal point backwards, 1, 2, that adds a 0, 3 adds another 0. That's my number, 0.0013. Has 2 significant figures in it because those leading zeros are not significant. Try this one. Well, there are 2 possible answers that you might come up with. One is 1, 5, 0, 0, if I move the decimal point 3 places, but that's got 2 significant figures, and I'm supposed to have 3 significant figures because that's what I have in my mantissa. So I could try it this way, 1500 with the decimal point, but that's got 4 significant figures, and that's wrong too. So what's the answer? Well, the answer is you really can't write this number without using scientific notation. So scientific notation isn't only a tool for saving us from writing zeros. Scientific notation is sometimes the only way we can properly express the precision that we have in a number using the significant figures rules. Now we need to talk about arithmetic using scientific notation. If you're going to add or subtract some numbers, the ends in both of the numbers have to be the same number. It's like comparing apples to oranges if they aren't. Once that happens, then you just add the mantissas. For example, let's say I was going to add 2.5 times 10 to the third to 2.50 times 10 to the fourth. It turns out that you're going to get better results if you have both of these numbers in the higher of the 2 exponents. So what that means is I want to take 2.5 times 10 to the third and change that to a 10 to the fourth number. Well, 2.5 times 10 to the third is really 2500. If I want to write that times 10 to the fourth, I would have to move my implied decimal point 1, 2, 3, 4 places back, which would make that 0.25. So 0.25 times 10 to the fourth is 2.5 times 10 to the third. So to make the exponent bigger, move the decimal point left. Could be a rule of thumb. Now, putting these 2 numbers together, 0.25 times 10 to the fourth plus 2.50 times 10 to the fourth, and adding, my exponents are going to be the same, 10 to the fourth. Now, it's clear to me where I should round my number. Both of these are good to the nearest hundredth. And so this is going to be 2.75 times 10 to the fourth. Multiplying is easier. When you multiply, you simply add the exponents and then multiply the mantisses. So let's say I was multiplying 5.0 times 10 to the third by 5.0 times 10 to the fourth. I multiply the mantisses. 5 times 5 is 25. I want that to two significant figures, so I write it down just that way, 25. And then times 10 to the 3 plus 4, because I'm adding the exponents. So that's to the 7th. Now this isn't in scientific notation anymore, so if I wanted to do that, I'd move my decimal point back one to the left. 2.5 times 10 to the 8th would be that number, because when you move the decimal to the left, that makes the exponent bigger. Dividing is almost as easy. You subtract the exponent in the denominator from the exponent in the numerator, and then you just divide the mantisses. So for example, say I was going to do 25.0 times 10 to the 5th divided by 5.0 times 10 to the third. Well, dividing the mantisses, I have 25 divided by 5, that's 5. And I should have two significant figures, because that's how many are in the bottom mantissa. My answer will just have 5.0 as the mantissa, times 10 to the 5 minus 3. Well, 5 minus 3 is 2. The other thing you can do is just learn how to use your graphing calculator. It's actually fairly easy to do problems like this and get them right all the time. Let's go back and do these last three problems using our graphing calculators. Adding or subtracting. We did this problem, 2.5 times 10 to the third plus 2.50 times 10 to the fourth. I don't have to convert exponents or anything if I use my graphing calculator. Remember, I'm using the EE button as my way of expressing scientific notation. So I'll key in my mantissa, my first mantissa, 2.5, and then second function comma puts that second EE in there. It's times 10 to the third, so I put that in as my exponent. Now I'm going to add to it 2.50, second function comma is times 10 to the, and then 4. And it automatically does my conversion for me, and it gives me 27,000. Now, I still have the problem of not knowing exactly where to round this answer to. Your calculator can't do that for you. For our multiplication, this was the problem that we did. 5.0 times 10 to the third was multiplied by 5.0 times 10 to the fourth. Doing it on the calculator, 5.0 times 10 to the third times 5.0 times 10 to the fourth. Calculator writes this down without putting it in scientific notation. We can force it into scientific notation by doing this. Go into your mode operations and then click on Sci and enter. This puts it in scientific mode, and then when we do this problem again, 5.0 times 10 to the third times 5.0 times 10 to the fourth, the answer is returned to us as 2.5 times 10 to the 8th. And here was our division problem. It was 25.0 times 10 to the 5th divided by 5.0 times 10 to the third. Let's put it in the calculator. 25.0 times 10 to the 5th divided by 5.0 times 10 to the third. The answer comes out as 5 times 10 to the 2. I have to be smart enough to know that I'm supposed to have two significant figures here, and so I'd write it as 5.0 times 10 to the 2, like we did last time. If you don't have a calculator handy, or you just want to get a quick answer, you can often, in science, do calculations that look really complicated and get a very, very close estimate to the answer by making use of scientific notation. For example, the problem that we're looking at right now, you might think that that's impossible to do without a calculator, but it really isn't. You can get very, very close to the correct answer in your head just by doing estimating. Scientific notation really helps us out here. The first step is write everything in scientific notation. So 2100 becomes 2.1 times 10 to the third. 0.032 becomes 3.2 times 10 to the negative 2, and that's squared. In the denominator, we have 6.0 times 10 to the negative fifth, and 9.4 times 10 to the 22 is already in scientific notation. The next thing you want to do is group the mantisses together and then multiply that by the exponents grouped together. So that'd be 2.1 times 3.2 squared divided by 6.0 times 9.4. I'm multiplying that by 10 to the third times 10 to the negative 2 squared divided by 10 to the negative fifth times 10 to the 22. Now the mantissa is going to be the least important of these two numbers. And so that's the one that you want to estimate. 2.1, I can write that as approximately 2. 3.2, that's about 3, and it's squared. 6.0 is really close to 6, and 9.4 is approximately 9. Now, exponents. 10 to the third, 10 to the negative 2 squared is 10 to the negative 2 times 10 to the negative 2, and in the denominator I have 10 to the minus 5 times 10 to the 22. Mantisses have been simplified, and we can see that we can simplify this even more yet. 3 squared is 9, so 3 squared and 9 cancel out. 2 and 6 cancel out to give you just 1 over 3. And so our new mantissa is 1/3 times, well, here's our exponent. In the top we have 10 to the 3 minus 2 minus 2. Well, 3 minus 2 would be positive 1, minus 2 more would be negative 1. In the denominator we have 10 to the negative 5 plus 22. Well, that's 10 to the 17. So our answer is 1/3, or approximately 0.33, times 10 to the negative 1 minus 17. So our answer is 0.33 times 10 to the minus 18, to two significant figures even. Let's see how that compares with doing this on the graphing calculator. 2100 times 0.032 squared divided by, I'll close this with parentheses, 0.00060 times 9.4 times 10 to the 22. Close my parentheses, hit enter. Almost the same answer. When you consider that the 10 to the minus 19th would have to be changed to 10 to the minus 18th if we had 0.38 instead of 3.8. So we're only off by 5/100ths in this mantissa, and we didn't even use a calculator.